Alright, time for a short, sweet, and to-the-point quiz review video. Listed before you are all the things that will be on the quiz on Monday. First, inertia. Remember that inertia depends only on mass. You can expect some really complicated question about inertia, where it's like, here are 5 objects, and I tell you a whole bunch of things about them, and then I ask you which one has the most inertia, and the answer is simply the one that has the most mass. So, to answer the inertia question, remember inertia depends only on mass. Inertia and mass. It will be a really complicated question, and it will come down to just remembering inertia depends on mass. And that's all I'm going to say about inertia in this video. Then you'll have to do calculating mass and weight. I'll do one example for you in the video tonight. Forces and free body diagrams. You had to know that was coming after we practiced free body diagrams so much. Vector addition is making a reappearance, so if you were bad at vector addition the first time around, or not necessarily bad at it, but had problems on the quiz the first time we did vector addition, might want to review that, and I'll do one example in the video tonight. And then the free response question will be about static equilibrium. And I will not do an example in this video, but I'm going to repost an old example that's a lot like the quiz problem. So, be ready for all of those things, and here we go. Alright, calculating mass and weight. So you can expect an AP level question, which means somewhat tricky, from this topic right here. Let's suppose I give you some kind of problem that says we're on another planet and we're going to use gravity on that planet. So I might give you a problem where there's a planet with gravity of 5 meters per second squared. Or rather, acceleration of gravity, 5 meters per second squared. And remember, that is little g. And then it would be a normal problem from there. You just have to recognize that the g is different. So pay attention to the question. Don't assume that we're always using the g from Earth, which is 9.81 meters per second squared. If the problem doesn't tell you where you are, you can assume it's Earth, but read the problem carefully because it might say you're somewhere else, and then you can't use Earth's acceleration of gravity. You have to use the acceleration of gravity of whatever planet you're on. So let's follow through on this example. Let's say we're on a planet where gravity is 5 meters per second squared, and we have a mass of 3 kilograms. Well, remember, first thing you're going to want to do is say, okay, gravity is given in meters per second squared, but my units will work out better if I convert meters per second squared over to newtons per kilogram. And that conversion is simple because a meter per second squared is a newton per kilogram. And we are not using gravity on Earth. I gave a different one. So now we can solve that weight problem. Weight equals mass 5. Sorry, mass is not 5. Let's just start over. Weight equals mass 3 kilograms times acceleration of gravity, 5 newtons per kilogram. Multiplying that out, you get 15 newtons. There we go. Remember, just pay attention. Unless it doesn't tell you about another planet, you should not automatically assume gravity is 10 newtons per kilogram in these problems. Read them carefully. Alright, then you're going to be asked to draw free body diagrams. So why don't you try drawing a free body diagram for each of these situations. In situation 1, we have a box sitting on a table. And let's make it more exciting. Let's say that that box has a velocity to the right. So I'll draw these little wavy lines to indicate its velocity. That's situation 1. Try that one. Then let's say we have a picture hanging from 2 ropes. Draw a free body diagram for the picture. And then let's say I have a box hanging from the ceiling, so this is the ceiling up here, by a rope, and a star hanging from the box. Give me a free body diagram for both the box and for the star. Why don't you pause the video, try those, and then come back and listen to the answers. Alright, hopefully you tried that. Here is the response. So for the box with a velocity to the right, I know that gravity is acting on it, so it has a force of gravity, or a weight. I know that sitting on it's sitting on a table, therefore it has a normal force from the table that keeps it from falling. And if it has a velocity to the right, friction is therefore acting on it to the left. Just because that box has a velocity doesn't mean it's being pushed. So don't be tempted to put a force on it to the right unless the problem specifically says the box is being pushed. Velocity does not necessarily mean it's being pushed. All right, now onto our picture frame. That picture frame has gravity acting on it. And it has a tension, let's see if I can get these lines small enough, yet still touching the dot to get two of them. Okay, you can see there are two lines there. And then there is a tension from each rope. That is my picture frame. Now on to problem 3. On the star, we have gravity acting on it. And let's label these ropes real fast to make this easier. I'll call this rope T1 and this rope T2. By the way, on a problem on the AP exam, if the ropes weren't labeled, you get to label them. And as long as you've labeled it clearly on the exam, the reader will know, okay, they've labeled the bottom rope T1, therefore anything that says T1 is that bottom rope. You can do the same thing on the quiz on Monday. All right, and then we have, if we move back to our actual problem, the star had gravity acting on it, and it has tension 1 acting on it. Now our box has gravity acting on it, pulling it down. Our box also has tension 1 pulling it down. Tension 1 is clearly pulling that box down. And then the box has tension 2 holding it up. And there we go. On to the next examples. So vector addition, I'll do a real fast example. Remember, if you have two vectors and you want to add them graphically, you have to take one vector and then have the second vector with its tail at the tip of the first. So the tip, when I say the tip of the vector, that is the pointy part. So on the blue arrow, that's the tip. The tail is the not pointy part. So on the red vector, this is the tail here. You take one vector, put it somewhere, same direction. You can't change the direction of the vectors. And then you just move the second vector so that its tail is on the tip of the first. And then your resultant vector goes from the tail of the first vector to the tip of the second. So the black vector is my resultant vector, from tail of first to tip of second. What a lot of people did wrong on the first quiz was when they drew their resultant, they went from the tip of the second to the tail of the first, and that is incorrect. So that orange vector is wrong. The black vector is the right one. Tail of the first to the tip of the second. All right. If you have any questions about that, be sure to call me or ask me, but we've done that before, so it should be pretty simple. Put the two vectors together with the tail of one at the tip of the other, and then draw the resultant from the tail of the first to the tip of the last. Moving on. In static equilibrium problems, if you do not set up your problem using up forces equal down forces and left forces equal right forces, you will most likely get that problem wrong. So when you get to the free response section and it says find all of the forces above, if you don't immediately write F up equals F down, F left equals F right, and then start categorizing the forces, so if I had a gravity force, I'd know that was down. If I had a normal force, I'd know that was up. Maybe friction would be left or right. If you don't write F up equals F down, F left equals F right, and start categorizing those forces and setting up equal to down and left equal to right, if you don't do that, just expect to miss the question. Not because I'm just going to mark it wrong if you don't do that, but the question is complicated enough. If you do not divide up your forces, you will get it wrong. That's all. In the next video, there is one static equilibrium example that's similar to the quiz.